Okay. All right, let's get going. Good afternoon. My name is Jerry Frankel, and today I'm going to talk to you about a subject that is near and dear to my heart, and that is corrosion, something that I think all of you should know something about, being engineers. So what we're going to do today is we're going to define corrosion. We're going to talk about why corrosion is important, a little bit of the electrochemistry of corrosion, some of the phenomenology of corrosion, that will end up, importantly, how we can prevent and minimize, protect against corrosion. So corrosion, I'm going to define today as the environmental degradation of materials. Okay? So we make materials, we design a part, we put it out in the environment, and its properties change. It degrades. Okay? So you're all familiar with rust, right? A pipe or a car, you see red rust, you know that that's corrosion. But there are other types of corrosion, there are other forms of corrosion that are fundamentally the same, and they look different. We'll talk about different forms. For instance, the patina that might form on a statue is corrosion. Okay, cracks that can form in important components, for instance, in nuclear power plants, are often the result of corrosion. We'll talk about that a little bit. Paint is used to prevent corrosion, but paint as a polymer can deteriorate when exposed to the environment, in particular ultraviolet light. Even very corrosion-resistant materials, like stainless steel, will corrode, and we'll talk about all of this. So corrosion is the interaction of the material with its environment in a way that degrades its properties. And this, but we rule out purely physical forms, such as erosion, galling, or wear, also can be very important, but those are not within the realm of corrosion. Okay, so you guys are engineers. Many of you are mechanical engineers. You're going to be designing things, right? And you've been learning how to pick a material, right? How to trade off things like strength and ductility. You might be thinking about cost, for instance. Okay, so you can pick that ideal material and design it, have it built, and put it into service. But you also have to be aware of how that service environment might change the properties of the material. So you might recall this accident, this disaster actually in Minneapolis a few years ago. I-35, there was a bridge that fell down into the river and several people died. Okay? And, well, the story was that this bridge was under-designed. Right? It was under-designed. Well, to me, if it was under-designed, the first truck that drove across it would have fallen into the river. Right? That's not what happened. The thing lasted 40 years. It was in good shape, more or less. It served as a bridge, and then it fell down. Something changed. Right? Something changed. You have already learned about some degradation processes, for instance, fatigue. Right? So if we apply a fluctuating or repeated stress, even at very low magnitudes, you can result in the degradation of the mechanical properties. You can also degrade properties by exposing to the environment. So for this bridge, what they've been saying is it was bird guano. Right? So whoever designed this bridge didn't consider how some critical parts would degrade as a result of environments to which the parts would be exposed. And what I am hoping to communicate to you today is that as you become engineers and go out into the world and design things, that you have to think about how the properties can change with time, not just what they are when the part is made. Okay, there is an annual cost of corrosion that's large. Okay? It's large. So if you think of a number, what number in dollars you think it is in the United States? Billions. Yeah, all right. It is billions. Turns out to be about 3.1% of the GNP. Okay? And in 2009, that works out to be $442 billion. $442 billion. Okay, so hundreds of billions of dollars used to seem like a lot of money. Nowadays, when we've got all kinds of large financial, economic problems happening, hundreds of billions of dollars are numbers that are thrown around. To put that into perspective, though, the annual budget for the U.S. military is $500 to $600 billion a year. Okay, so this is the direct costs of corrosion. There are indirect costs that are about equal in magnitude. Okay, so these are dollars that are essentially being wasted, where we have to repair bridges continually, right? And that money could be spent in other ways. So the cost of corrosion is very, very large. You can learn more about it. The last big study was done, and it's at this website. Interestingly, they, in this study, picked out an area. I mean, you know about the corrosion of bridges or cars, but what they picked out as one of the largest areas, the largest in fact, was utilities. For instance, drinking water and sewerage. Okay? So we use pipes to bring water to houses and sewers to take it away, right? And it turns out that the cost of failure of these components is huge. In the city of Columbus alone, there are 500 water main breaks a year. 500 water main breaks. So what happens when a water main breaks? Well, it was about 3 years ago, water main broke under High Street. The convention center got flooded. Okay, you might remember this. It was in the news for several days. What happens? You have to shut down the street, dig it up, fix the pipe, fix the street, okay? And then, somewhere down the street, the same thing can happen, okay? We have these old structures in place, and it's a real problem keeping them going. So you can imagine these costs. There also are safety considerations with corrosion that have to be considered, because corrosion can have catastrophic consequences, as can other materials failures. But corrosion is often a form that isn't found until there's a big problem. So here, for instance, is a big problem that happened. Aloha Airlines used to be an airline that flew around the state of Hawaii. So it was an island hopper. You could go from one island to another. In 1988, there was this incident where a large part of the fuselage of a plane ripped off in flight. Okay? One flight attendant was sucked out, but the pilots were able to land the plane. You can see people are there in some sort of condition. There was only really one fatality. But when they tell you to keep your seatbelt fastened, it might be a good idea. This was a corrosion problem. Okay? That had to do with maintenance of the airplane, aging aircraft. These aluminum alloys that are used to make airplanes are very susceptible to corrosion. Okay? So you can imagine if you're flying an airplane, you want to make sure that it's not corroding. There are other components that are equally critical. Boilers are essentially pressure vessels. So if you take a fluid and boil it and create a pressure, and that component corrodes and explodes, you can imagine there can be a lot of problems associated with that. Those of you who are Navy ROTC out there, and you want to be pretty confident that your vessel or your submarine is not degrading by corrosion in the sea, which is a big problem. Waste containers, and by waste I mean large industrial waste or nuclear waste. I'm involved with nuclear waste storage, so there's a lot of issues involved with long-term and short-term disposal of nuclear waste, and it's being held now underground in tanks. Okay? And you can imagine that these are structures that we don't want to fail and corrode, and they have in the past and leaked a lot of radioactivity. Okay? And ultimately, we need to find a way to store nuclear waste safely for a long time, 100,000 years or so, and make sure that it doesn't leak, and that will involve metal canisters that don't corrode. Bridges, we talked about a little about power plants. So power plants are environments that can cause corrosion. Some of you might remember Davis-Besse, a plant up near Toledo here in the state of Ohio that had a corrosion, a famous, infamous corrosion problem. Aircraft we talked about here, and turbine blades, another part of the aircraft where a form called hot corrosion can occur. Important when flying in the desert, as some of our military planes are doing. Okay, so corrosion can have these catastrophic consequences, again, often because it goes unnoticed. There's corrosion sites that can lead to rapid failure. Okay, so let's talk a little bit about the electrochemistry of corrosion. These are some things you learned about in chemistry in high school and in chemistry here at Ohio State, so I'll just be refreshing you about some of this chemistry. You might have done this experiment in high school chemistry where you put a piece of zinc into an acid solution, and what happens? Well, it corrodes. There are bubbles that form and vigorously come off the surface. How many people saw that in high school chemistry, that kind of a thing? Okay, so what's happening when you put zinc in an acid? We put zinc, reacts with HCl, forms a zinc chloride product plus this hydrogen gas. Actually, in a simplified form, the zinc is reacting with the H plus ions that are in the acid to form zinc ions. Okay, so the zinc here, zinc metal atom, forms a zinc ion. Okay, and that, this, by the way, isn't balanced. We need to balance our reactions, right? And form H2 gas. Okay? So this is a cell reaction that describes the corrosion of zinc and the evolution of hydrogen gas. And in fact, there are two parts to this reaction. There's the zinc oxidation reaction, zinc going to zinc 2+, and that releases electrons. Okay? There's a change in oxidation state. That's a 2+. No, sorry about my writing there. That's a 2+. Zinc becomes a cation in solution. It releases electrons, and that's the oxidation reaction. And there's the degradation of the zinc is the result of that reaction. However, that reaction can't occur by itself. These electrons that are released by that reaction have to be consumed by a reduction reaction. Okay? That's at the cathode. Reduction reaction at the cathode would be the other part of this, the 2H+, reacting with those two electrons to form hydrogen gas. Okay? So that's what's happening here. H+ from this HCl solution. The HCl goes to H+ and Cl-. H+ makes an acid. 2H+ get together to form H2 and consume those electrons. So we have an oxidation reaction and a reduction reaction that are part of our corrosion overall cell reaction. So I'm going to give you a little simple mnemonic. A mnemonic is a memory device here to help you remember that loss of electrons is oxidation. So loss of electrons would be some metal. We use a metal M here. That's a generic metal. Of course, there's no metal M. Let's say that's oxidizing to form 2E-. Loss of electrons is oxidation. Gain of electrons is reduction. So that would be the opposite of that. We could, in fact, plate out metal ions, or I showed you the reduction of H+ to form H2. Okay? So reduction is a gain of electrons. Oxidation is a loss of electrons. And here we have Leo the lion saying grr. Okay? Again, the idea is to remember we have an oxidation reaction, a reduction reaction. The two of them combine in a corrosion cell to form a total corrosion reaction. Leo the lion says grr. Okay, so we have an electrolyte. Electrolyte is our environment in which corrosion is happening. Okay? Electrolyte is an environment, and the electrolyte contains various species. There are ions, okay, positive and negative ions. A cation is a negative ion. Okay, so chloride would be one, OH- would be one. A cation is a positive ion. Okay, so we talked about H+, and there are metal cations. right? Fe2 plus, that's iron, nickel 2 plus, aluminum 3 plus, aluminum 3 plus. Okay? Metals in their typical oxidation states. Okay? We could have sodium around. We had a sodium chloride solution, which is essentially what seawater is. So we have to have an electrolyte that's aggressive and capable of carrying electric current by the movement of ions, okay? Because that's going to be part of our circuit. And we need an anode and a cathode, okay? So anode is where the atoms lose the electrons to become positive cations. That's where oxidation takes place. The cathode is where reduction takes place. Okay, so those are some definitions. We have an electrolyte, we have an anode, we have a cathode, and those in fact are the requirements for corrosion. Okay? For corrosion to occur, we need to have an anode or anodic sites on a metal. Okay? That's where the oxidation happens. We need a cathode or cathodic sites on a metal. That's where reduction happens. We need an electrolyte that provides ionic conduction. Electrolyte contains ions, and we need an electrical connection to allow the electrons to flow. Okay, so if we had two metals, here's a metal that's an anode and a metal that's a cathode. They're immersed in our electrolyte that contains ions. Okay. At the anode, metal dissolves. Okay, so again, we're just using a generic metal M here. It's happening at the anode, releases electrons. The electrons flow through this electrical connection over to a cathode where we have a cathodic reaction. Okay, cathodic reaction, one of which I showed you before, this hydrogen evolution reaction, H plus combining with electrons to form hydrogen gas. In an aerated environment, like this one here, this is an aerated electrolyte, this is my water. Contains anions and cations, right? It has some minerals in it. It also contains oxygen. It's exposed to the air, contains dissolved oxygen. That oxygen can react with water and electrons to create OH minus. That should be a balanced reaction. Okay? And so that's consuming those electrons, creating OH minus on its surface. So we have electrons flowing through there, and in fact ions flowing through our electrolyte, completing this circuit. Okay, so there's a complete circuit here for charge to flow. Corrosion is like a battery. Corrosion is a battery, okay, except in a battery, like the battery that's running this laptop, we break this connection and put some load in there, right, like the laptop, and we collect that energy. We collect the energy of the reaction. In corrosion, it's like a shorted battery. It's like you take the two terminals of your battery, connect them with a wire. What happens? Well, you lose the charge, right? You lose the energy. The battery becomes useless. That's what corrosion is. It's taking the energy we put into making the metal and losing it. Take the energy we put into a battery and losing it, just throwing it away. Now, these can happen on a single metal surface. We can have an anode and a cathode on a single metal surface. Electrons flow from the local anodes to the local cathodes, and we have this flow of charge in the electrolyte. So we still have our local circuit happening here, and it happens on one metal surface. Here we have two metal surfaces. This is galvanic corrosion, when we have two different metals that are in contact. I'll talk about this later. But these anodes and cathodes can be on a single metal surface, and if they move around the surface, we end up with general corrosion, eventually eating up that whole surface, and the thing dissolves away, which is what happens when we immerse that zinc into the acid. Okay, so much for electrochemistry. That's it. Okay, that's the end of the chemistry. You can breathe a sigh of relief. What I'm going to talk about now really is the phenomenology of corrosion. Okay? There's a lot of interesting phenomenology, and one of the important aspects of corrosion is this notion of passivity. It turns out that many important metals are resistant to corrosion because they're passive. We call them passive. What happens is they form a very thin oxide film, usually nanometers in thickness, on their surface that protects them from the external environment. So we have an environment, an aggressive environment out here, but this thin oxide layer that forms spontaneously, naturally, just upon exposure to air, forms on that surface and creates a barrier and protects it. Okay? So aluminum alloys, nickel-based alloys, stainless steels are typical. So if we consider this sink, for instance, over here, it looks like it's metal, right? Looks shiny. It looks like it's metal. Actually, it's covered by a thin oxide layer. Stainless steel looks like it's metal. It has a nanometer thick oxide layer on it. You can't see it. It's so thin. But that's why it's corrosion resistant. It forms a protective oxide film. Okay? So stainless steel, let's talk about stainless steel for a moment. Stainless steel is a steel. Okay? That means it's iron-based. Iron-based alloy. You learned about iron and steel. Okay? If you add chromium, more than 12% chromium, you can form this stainless steel. So this is actually really cool. Chromium is very expensive, right? We can get the corrosion resistance of chromium by putting in a small amount of chromium into our alloy, and we end up with a chromium oxide layer on the surface. Even though there's some relatively small amount of chromium in the alloy, it behaves more or less like pure chromium. Okay? We get this very corrosion protective coating spontaneously formed on the surface. Okay? So the garden variety of stainless steel, if you go to the hardware store and get a bolt, stainless steel bolt, it'll be 304 stainless steel. It has 18% chromium, so more than the minimum. The minimum is 12% to form this layer. 18% chromium and 8% nickel. 8% nickel. So we add nickel. Nickel adds some corrosion resistance, but importantly, what nickel does is to lower the eutectoid transformation temperature. So you learned about eutectoid transformation, where austenite, the gamma austenite, turns into alpha ferrite and cementite, Fe3C, right? Or when they're combined, that's pearlite, right? So that happens at the eutectoid transformation temperature. If you add 8% nickel, that temperature goes down below room temperature. So the FCC structure is stable at room temperature. Iron and chromium are both BCC metals, the pure forms. When we add 8% nickel into this alloy, it becomes FCC, face-centered cubic. Okay? And face-centered cubic materials are more ductile. They have more slip systems. They're easier to work. Okay? So this gives us a ductile material. We can form things. It has corrosion resistance. Okay? So it's a good corrosion-resistant material. Interestingly, if we want to make a knife, stainless steel knife, we don't want to make it from a face-centered cubic structure. We want a knife to be very hard, right? We don't want a knife to have a lot of slip systems that can be ductile. We want the knife to be hard, so it isn't austenite, right? And you know that because the knife, in my kitchen, we attach it to a magnet on the wall. The FCC phase is not magnetic, okay? But the BCC phase is magnetic, or in fact, we can form martensite and tempered martensite to get that hard edge on a knife. Okay? The handle, if it's a stainless steel handle, will be an FCC material for forming and corrosion resistance. Okay, so 304 stainless steel, 18% chromium, 8 nickel. We get a protective chromium oxide layer on the surface. If we need more corrosion resistance, if we have a more aggressive environment than our kitchen, let's say, we can add more alloying elements. If we add 2% molybdenum, the next step up is 316 stainless steel. Very corrosion-resistant material. Okay? But we can add more things. We can add more molybdenum, more chromium. We can add tungsten, and in fact add more nickel and take away the iron. And we end up with extraordinarily corrosion-resistant materials. Nickel-based alloys with 25% chromium, 6% molybdenum. We have several percent tungsten. And these materials are protected by thin oxide layers on the surface, extraordinarily corrosion-resistant. You might even store nuclear waste in them for 100,000 years. Okay? Phenomenon of passivity is a critical part of corrosion. All right. So we've learned about passivity, and I want to talk to you about different forms of corrosion. Remember at the beginning I said that corrosion doesn't all look like red rust, that there are different forms of corrosion that look very different, that follow the same underlying mechanisms, the same anodes and cathodes, right? The electrochemistry is the same, but it looks a lot different. So this uniform corrosion might be, a red rust that you see on a signpost, for instance, that, that down at the ground because of the salt will be corroded, or a heavily corroded car. We talked about galvanic corrosion, and I'll be talking about most of these in the upcoming slides. You can read details about this in the chapter in Callister. It has some good descriptions of the different forms of corrosion. So let's talk first about galvanic corrosion. I described this at the beginning where we had different metals that were connected by a wire in the same environment. In fact, those are the requirements for galvanic corrosion. They're the same requirements for corrosion, except we have two different metals electrically connected in the same electrolyte. And the result of the galvanic corrosion is that one of the metals corrodes faster and the other one corrodes slower. It means it's protected. In fact, I'll describe at the very end how we make use of galvanic corrosion to reduce corrosion. We use it for protection. Okay? And here we have an example here. This is a copper pipe that is soldered. So this part is copper here, this part is steel. They're soldered together, exposed in a corrosive environment, and we have a lot of heavy attack in the steel, right next to the copper. Okay? Steel is heavily attacked. So how do we know when we connect two metals which one's going to be attacked? Well, the more anodic metal will corrode faster, the less anodic metal will corrode slower. Well, what's that mean? Well, we can look in a galvanic series that'll tell us which is which. That's what this is here. The galvanic series is this ordered list of relative nobility of alloys. Okay? So at the top we have the more noble or cathodic. Okay? More noble or cathodic. So up here we have platinum. Gold would be up here. Silver. So these are noble elements that we use for jewelry, for instance, because they don't corrode. They in general are very corrosion resistant. Okay? Up here also is stainless steel. When it's protected by a passive layer, it behaves like these very corrosion resistant materials. Titanium, very corrosion resistant. Down at the bottom, we have the more active, less noble, or they are anodic. Okay, so down here we have very reactive metals. Magnesium. The zinc, we talked about how it reacts. Magnesium is explosive. We actually, we make fireworks out of magnesium. Aluminum is down here. Steel is down at the bottom. Steel is very reactive. Okay? It's less noble. So what happens is if we connect any of these two like that, okay, if we connect, let's say, titanium to aluminum, in a galvanic situation, in a corrosive environment, titanium will be protected, the aluminum will corrode faster. It will corrode faster than it would if it were not protected. Okay? So the alloy that's higher will corrode slower. The alloy that's lower will corrode faster when we connect them together. Okay? So this galvanic series is a way of judging which one will corrode faster or slower, just by looking where it is on this series. And this is in seawater. Could change in other environments. Seawater is a common corrosive environment. So we talked about pipes, big things that can experience galvanic corrosion. galvanic corrosion is also a problem with very small things. Okay? This is the structure of magnetic recording heads. So hard drives like the one that's in this computer are little discs of metal that have very thin layers on top of that metal disc. Okay? Those magnetic layers on that disc have little bits of magnetic domain that face one way or another. Okay? That's the information that's being stored on this disc. And that information has to be written onto the disc, has to be read from that disc using these little recording heads that fly above this spinning disc. Okay? The structure of these heads is very specific for physics reasons to get to be very sensitive sensors for magnetic bits of magnetic information, little magnetic fields. Right? And to get higher and higher densities, to get larger and larger disk drives, which is what's happened for decades, right? Disk drives get larger and larger. The way you do that is to make the magnetic domain smaller and smaller. So you need very sensitive sensors. And here's a structure of a very sensitive sensor. It's called a spin valve. And we see that there are layers of different materials that are put down on top of each other. Okay, we have cobalt and copper, for instance. Cobalt is down towards the bottom of that galvanic series. Copper is well above it. And what happens actually is a cross-section. This cross-section of all these layers gets exposed on the surface of this sensor. Okay? It's more or less exposed to the environment. So we can see that this is a galvanic corrosion nightmare. All these materials are all connected together. They're deposited right on top of each other. They get exposed to the same environment. Okay? And some of them are very susceptible to corrosion. So electronic devices, magnetic storage devices, are actually very susceptible to corrosion. And the moral of this story is to back up your hard drive. Okay? Because corrosion will happen. Right? Corrosion will actually, missing bits of information isn't the problem. The problem is that you get little mounds of corrosion product and the head slams into it and then the hard drive crashes. Okay? And if you haven't had a hard drive crash yet, you probably will someday. Back up your hard drive. Galvanic corrosion is a big problem in electronic structures because the people that design them like to combine all different types of materials together for their electronic properties, their magnetic properties, and their optical properties. Okay, pitting corrosion. We're going on to these different forms of corrosion, right? Galvanic corrosion was the last one. Next is pitting corrosion. Remember, I talked to you about how many metals have this thin oxide layer that's a passive film protecting it, right? And it's really wonderful. This thin oxide layer gives it corrosion protection, and that's great. The problem is that these very thin oxide layers, remember, they're nanometers in thickness, right? You can't even think about how thin a nanometer is. They're susceptible to local breakdowns, local breakdown in that layer, and it exposes the metal underneath. The metal itself is rather corrodable, right? So in stainless steel, you have iron in there. It's corrodable material. Or aluminum is extremely corrodable. It's protected by aluminum oxide. Well, once you get a breakdown in that film, it can lead to accelerated dissolution at the point of the breakdown. So you get local breakdown of the otherwise protective passive film and accelerated dissolution at that point. So the attack is very localized. And here, this is stainless steel. Okay, stainless steel exposed to an aggressive environment, and we can see that it doesn't look very stainless, right? It's getting attacked, but the attack is very localized at these spots here. The problem is that on a big structure, these little pits are difficult to see. It's hard to inspect and find them. So this is the kind of form of corrosion that can lead to a problem. It can lead to perforation. It can lead to a stress concentration that will initiate a crack. Okay? Chloride ions are aggressive species that are often involved with initiating this type of attack. And chloride ions, as I said, are in seawater, and they're all over the place. So we put salt on the roads, right? That's chloride. We have seawater, there's sweat, there's salt all over the place. And chloride is almost always the cause of localized corrosion. And we have pits here formed by the local breakdown of this protective passive film, leading to accelerated dissolution. That's an interesting and important form of corrosion. A related form is crevice corrosion. So crevice corrosion happens at a shielded area, okay, a crevice. So here's an example. This is a piece of stainless steel. This is this 316 stainless steel, very, very resistant to corrosion. Well, it was exposed to this acid condensate, and here's a hole. There's a bolt that went through that hole, and a washer, okay, a polymer washer was pressed against the surface by this bolt. And you see that the area that was not under the washer was not heavily attacked. In fact, we have some numbers that were stamped into the surface for identification. They look fine. Okay? But the corrosion, rather severe corrosion, happened in this creviced area. Okay? In the area underneath the washer where there was a limited access of the exterior environment. That's a crevice. And in that region, we have essentially these same reactions that happen in a pit. In fact, they're easier to happen in a crevice. So if you can design structures without crevices, structures that are going to be in corrosive environments, try to design them without crevices that can cause this type of corrosion. Intergranular corrosion is another form of localized corrosion. Okay? And this is an aluminum alloy. It's actually a cross-section of a sample. That's a cross-section. So there was a plate. This was a plate that went, in and out of the screen here. Okay? And the top surface of that plate was exposed to an aggressive environment, a corrosive environment, and the back side here was not exposed. Okay? It was exposed for some period of time, and then it was cross-sectioned and polished. It wasn't etched. So you've been looking at etched microstructures. Etching is a corrosion reaction that brings out the grains. This was not etched. It was just cross-sectioned. And we see that just by cross-sectioning, there are gaps, regions where corrosion came in through the grain boundaries. The grains are unattacked. The region between the grains is attacked. Okay? So you can see that it, in fact, made it all the way from the exposed side to the unexposed side. Okay? And this type of structure, you could imagine, wouldn't have much mechanical integrity, right? It wouldn't have strength. It would fall apart quite nicely. So intergranular corrosion is corrosion along grain boundaries because of a difference in composition. So this aluminum alloy had a region near the grain boundary that was much more susceptible to corrosion. This can happen in stainless steels, and there's a phenomenon called sensitization where that chromium, stainless steels contain chromium, it enriches to form an oxide on the surface, but in a certain temperature region, there's a depletion of chromium near the grain boundaries because chrome carbides form. And this can happen during welding. Those of you who are going to become welding engineers will learn a lot about this. If you weld stainless steel, you have to take care because the area near the weld can degrade enormously at grain boundaries. So what happens is the grain boundaries act like regular carbon steel, gluing together corrosion-resistant grains. An attack like this will happen, an accelerated attack through those grain boundaries, so you lose the structure of the material. Okay, the final form of corrosion I'm going to talk to you about is environmentally induced cracking. This is the interaction of stress and the environment. Okay, so we have a combined effect of environment and stress, and we see that normally ductile metals can be very brittle. This is brass. Brass is an extremely ductile material, and we see very sharp cracks when this brass is stressed in an environment containing ammonia. Here's steel. Carbon steel can, under most circumstances, exhibit a lot of ductility. Here we have intergranular cracks, cracks along grain boundaries. And these can happen at stresses well below the yield stress. So again, these are stress regions where we would expect elastic type behavior. not plastic deformation, not failure, low stresses, and yet we have cracks forming. Okay? Very specific environments, chloride again with stainless steels, ammonia and brass, caustics. Caustics means high pH and hot usually. Okay? So we have this, and this is a very important form of corrosion because these cracks can grow very rapidly. This is the fastest growth form of corrosion. We get cracks growing extremely quickly because of the interaction of the stress. Okay, we have a tensile stress in a corrosive environment, and there's dissolution at the crack tip that accelerates that crack growth. Okay, very, very important form of degradation. Fatigue, you learned about fatigue. Fatigue, crack growth is accelerated in a corrosive environment. Okay, so again, the bottom line is that when you design something for mechanical properties, you want to make sure that the environment in which it's going to be serving is not one that in which this material will become susceptible to cracking by stress corrosion cracking. Hydrogen embrittlement is this hydrogen gets in the metal and embrittles it. Corrosion fatigue is when we have this varying stress. Okay? And altogether it's called environmentally induced cracking. The environment causing, accelerating cracking under conditions where you would have normally a very ductile material. I want to say just a few words about corrosion rate determination. Okay? So we have a unit here for corrosion rate, which is mils per year. A mil is a thousandth of an inch. So in the United States, we like to use inches. So a thousandth of an inch per year. And there's an equation that's given in the book where the corrosion rate in mils per year is given by 534 times W, okay, where W, let's say you take a sample and you immerse it into, like this, into an environment. W is the change in weight, the initial weight minus the final weight. Okay, so it's some change in weight in milligrams. Okay, we divide that by rho, its density, in grams per square cubic centimeter rather. The exposed area on all those surfaces in inches squared, and the time in hours. Okay, and what this does is a weight per unit area per unit time. The density turns it into a depth per unit time. This 534 just allows these units to cancel out. So you get all these weird units combining, and they end up with mils or thousandths of an inch per year. Okay? And if it's less than a mil per year, that's generally considered to be a good corrosion rate, or a very good corrosion rate. Okay, in the time that remains, I want to talk about the most important part of this, which is minimizing or reducing corrosion. Okay? So what do you do to prevent corrosion? Well, you can use a more corrosion-resistant material. You can look up generally the corrosion properties and corrosion rates in handbooks for a given environment. The problem is that more corrosion-resistant materials, those that passivate, usually are more expensive. Okay? So we can add chromium, we can add elements, or pick a material that's very corrosion-resistant. Usually, they're more expensive than those that are susceptible to corrosion. But again, if you're considering lifetime costs, you want to use something, you want to design with a material that's going to survive for the lifetime. If possible, remove aggressive species from the environment. If your environment is seawater, well, you can't do that, right? You can't remove chloride from seawater, but there are many environments, process environments in the chemical industry, for instance, where you, cooling water, for instance, there's recirculated cooling water is an environment that can cause corrosion. Well, you want to take out the corrosive species if you have control of your environment, or you can add a chemical that inhibits corrosion. So that recirculated cooling water, we add chemicals that are called inhibitors. Okay? The antifreeze that you put into your car contains corrosion inhibitors. to prevent corrosion of your cooling system. That system is a recirculated water cooling system. Okay? And if you just put water into your radiator, you use water and not Prestone antifreeze, you're going to get corrosion. You're going to have to replace your radiator. So don't do that. Separate the metal with a barrier layer. Paint. This is probably the most common way that we prevent corrosion. We paint things, right? We paint our cars. We paint bridges. Okay? The problem is that paints degrade. As I indicated at the beginning, paints degrade. You have to repaint. Remove crevices from the design. Crevices accelerate corrosion. Minimize galvanic corrosion susceptibility by using materials that are close on that galvanic series or electrically insulating. Chrome bumpers these days are electrically insulated from the car so that they don't cause corrosion of the steel car panels. They used to. Those cars in the 50s had corrosion around the bumpers because they didn't do that. Okay? Finally, the last thing is to use sacrificial or cathodic protection. This is where we use galvanic corrosion to our benefit. We coat with zinc. Okay? The zinc corrodes preferentially and protects the steel. So this is great until the zinc corrodes away, and then you end up with rusty farm roofs once the zinc corrodes away, right? The barn's roofs are galvanized. Or we can force a current between an anode and a cathode. You force the corrosion force the current to go in the direction opposite of corrosion. You reduce the corrosion rate. We do that with buried steel pipelines, which are crisscrossing the state of Ohio. Okay, if they are not protected, they can leak and corrode and explode. You remember San Bruno, California? There was a big fireball that burned down a neighborhood because of corrosion of a pipeline. Right? We have to prevent corrosion of these things. So when you go out there and design things, think about corrosion. Think about the environment that you're going to be in. That's it.